Welcome back! In this video we are taking on a tricky topic, infiltration. We are moving from a simple idea that air leaks into a building to the actual numbers you can use to quantify it. We'll connect the physics of airflow through tiny cracks to practical concepts like effective leakage area and air exchanges per hour. Here's our roadmap. We'll start with the basics, defining infiltration and what it drives it. Then we'll look at the physics of how air moves through a single crack. After that, we'll scale up to the entire building with the power law and the effective leakage area concept. We'll then use those tools to estimate airflow and air changes per hour. Finally, we'll introduce a handy shortcut and talk about the importance of being transparent about the uncertainty in our results. By the end of the video, you will be able to define the key metrics we use to quantify air leakage, ELA and ACH, and the power law model. You will also learn the skills to estimate the airflow and equivalent EUA from simple inputs. And most importantly, you'll be able to communicate the uncertainty in your assumptions, which is a key part of a good building simulation. To start, let's start with a question. Imagine you can't see air, only its effects. A door that pulls shut, a flickering paper, or a cool streak across your skin. These are all clues that reveal the invisible pressure difference and leak paths that drive outside air into a building. In this video, we are going to turn those everyday clues into actual numbers and explore the different forces that cause air to move. We will focus on a single but powerful question to get our intuition working. On a windy day, if you crack a classroom window, how much outdoor air do you think sneaks in? Is it enough to completely refill the room? Or it's barely a teacup? By the end of this video, you will be able to answer the questions like this yourself. You will be able to estimate the airflow from simple inputs, and you will know when a quick calculation is enough versus when you need a fuller treatment. Let's start by clarifying some key terms. Ventilation is the air you want. It's the intentional controlled outdoor air that's designed to come into a building. Infiltration, on the other hand, is the air you don't want. It's the uncontrolled leakage through all the cracks and gaps, and is driven by two main forces: wind pressure and the stack effect from temperature difference. The core physics here is the pressure difference and how that pressure pushes or pulls air across the building envelope. The magnitude of that pressure difference depends on a few things, like how windy it is and how tall the building is. The distribution of leaks also matters. A leaky basement has a different effect than a leaky roof. For our load calculations, we'll make a few key assumptions. That conditions are steady over a short period and that the air inside the zone is well mixed. This allows us to simplify our calculations and get the numbers we need without having to track every little change. Let's get even more specific about how that pressure makes air move. Let's zoom in on a single crack. The way air moves through it depends on the pressure difference. For very small pressures, the flow is laminar-like, meaning the flow rate is directly proportional to the pressure. Think of it as a smooth, predictable flow. But as the pressure increases, the flow becomes more chaotic and turbulent, behaving like an orifice. This means the flow is not proportional to the square root of the pressure difference. Since real buildings have countless leaks with all kinds of shapes and sizes, they actually behave as a blend of these two extremes. To model this, we use a single power law that neatly summarizes the entire building's leakage. This law uses an exponent of about 0.65, which is a perfect middle ground between the two flow types. Now that we look at how individual cracks behave, let's zoom to the whole building and see how we put all the information to work. We just saw that individual leaks can be tricky, but the good news is that at the building level we can simplify things. The power law with its parameters C and M is a powerful way to summarize all the thousands of tiny leaks into a single, comprehensive model for how a building responds to pressure difference. To make this even more practical, we use the concept of effective leakage area, or ELA. ELA takes that complex network of leaks and condenses it into a single imaginary hole. If you were to create a single opening with an area equal to the ELA, it will pass the same amount of air as the entire building at a specific reference pressure. This gives us one simple number to describe a building's overall tightness. We can figure out a building's C, N, or ELA by running a pressurization test, which helps us calibrate our model to the real-world performance of the building. Now that we have a way to describe a building's leakage, let's see how we use it to get real numbers. To estimate the actual airflow rate, or we have to figure out the total pressure difference acting on the building. We do this by combining the pressures from the stack effect, driven by temperature difference, and the wind, driven by wind speed. Once we have the total pressure number, we can use our ELA or the building's power law to calculate the volume of air flowing into the building. With the volumetric flow rate in hand, the final step is to calculate air changes per hour, or ACH, which is a more intuitive way to understand how much air is leaking. It simply tells you how many times per hour all the air in the room is replaced by outdoor air. It's a great metric, but remember, the number you get is only as good as assumptions you put in, so it is always important to be clear about your inputs. So we have covered a lot of ground in quantifying infiltration, and now we are at the point where we can make it really useful for our simulations. Now for a handy shortcut. For those quick sanity checks, or when you are just focused on the sensible load, you can convert air exchange into equivalent UA value. This is a great way to turn a messy airflow problem into a simple heat conduction problem, which is perfect for early stage design estimates. As a result, this shortcut is best used for a quick sanity check, or when a moisture and dehumidification are not a critical part of our analysis. When humidity control or dehumidification is a concern, you will need to use more detailed enthalpy-based methods. Finally, because infiltration is so variable, it's essential to be transparent about your inputs. In your reports, be sure to document your assumptions, such as the building's thickness class, its number of stories, and any wind shielding assumptions. This clear documentation makes your estimates more reliable and defensible, so anyone looking at your work knows exactly how confident they can be in your results. To wrap up, remember these three key takeaways. First, remember that the complex network of leaks in a building can be neatly summarized by a single power law, with an exponent of around 0.65, a perfect middle ground between laminar and horiphase flow extremes. Second, think of ELA and pressurization tests as your best friends for quantifying infiltration. They allow you to calibrate your model to the real world and get reliable estimates for V and ACH. And third, the UA equivalent is a fantastic shortcut for doing sensible only load approximation, but always state your assumptions so that others can understand the confidence of your results. This was our video. To go deeper, I invite you to continue learning about building energy calculations. You could explore shielding classes and pressure coefficients. These concepts show you how a building's surroundings, like nearby trees or other buildings, shape the pressure fields around its facade. By understanding this, you can make your pressure difference estimates and your infiltration models even more accurate. You could also dive into multi-zone airflow networks model. These advanced tools treat a building like a network of connected zones, allowing you to solve for airflows and pressures in much more complex structures. This is the next step to extend the concepts we use here to larger real-world buildings. Finally, consider learning about uncertainty propagation in load estimates. This helps to quantify how the variability in inputs like wind and temperature translates into a range of possible values for your infiltration estimates. It's a key skill for providing a defensible analysis. Thank you for watching. This video has given you the foundational knowledge to turn an invisible problem into a solvable problem. We hope these tools empower you to create more accurate and transparent building simulations. Thank you. Bye.